Yo, VIP. Let's kick it. Ice, ice, baby. Ice, ice, baby.
Why, hello again. I didn't see you there. Let's do a problem about ice tables. How does that sound? Okay. Alright, so check it. Here is a problem. I made it up myself. It's amazing. Take a look at it. If you don't mind, it would be appreciated if you pause the video, assuming you can see this okay, and try this problem yourself. See how far you can get. If you can solve it yourself, hey, awesome. If you can't, then keep on watching. So go ahead, pause it, do the video. Go on, pause. It's like down over here, pause. Yeah, okay. Alright, so I'm gonna assume you did that. Good job. Now, let's see how you did. So, let's actually walk through this problem. We call these type of problems ice table problems because we make a little chart and it has initial concentration, change in concentration, and equilibrium concentration, the first letters of which spell ice. Alright, so let's do that. First, let's talk about this problem. So we're given a Kc here, and just looking at this Kc, 1.25 times 10 to the 6th, that's a decently large number. When you see that number, when you see any K number, my batteries run out, so that's not good. Well, I'll keep talking until I'm cut off, I suppose. Alright, so when you see any K number, then you need to analyze that. In this case, is K less than 1, equal to 1, or bigger than 1? Hey, it's hugely bigger than 1. So that should tell you this is going to be product favored. So that's a starting point. Now the first thing that we need to do when we have this type of problem is, even before we get into the ice table, is to figure out Q so we know which direction we're going to go. Notice that we have 3 concentrations given: 0.7 molar, 0.04 molar, 0.18 molar. The fact that none of these are 0 indicates that, well, we don't really know which way we're supposed to go. Granted, if one of the products were 0, for example, we'd know, hey, we need to make more products. Or similarly, I suppose if the reactants were 0, then it would only make sense to do this type of problem if it was going to go back towards reactants. But when you're given some of everything, then you definitely need to solve for Q, and you definitely need to make sure that you are solving for it before you get started. So let's go down a little ways, or yeah, let's just grab another piece of paper and find Q. All right, here we go. Whoop. So you will recall, or maybe you won't recall, but you will see that we have values for Q and we have our reaction. So what is Q? Well, the whole point of Q, our reaction quotient, is to compare our values of Q to our values of K. Let's write it out. So Q is equal to the concentration of our products to the power of X divided by the concentration of... And we're back. Alright, so yes, Q is equal to products to the power of X over reactants to the power of Y. For our given reaction here, whoop, our products are over here. Do not forget, we use it to the power of our coefficients. So I'm going to say that again. As we write this, we need to make sure not to ignore these coefficients. They're going to come up again and again, and if you skip steps, like I like doing, then you will forget to use them over and over again too, and your answers just won't be right. So, try not to skip steps, as tempting as it might be. These all look pretty similar, but I don't know about you, I just can't keep these coefficients in my head all the time. And if you miss it even once, you may be in for some trouble. So alright, let's get to it. We have the concentration of our products up top. We have H2 as a product. This 3 becomes an exponent. H2, concentration of H2 cubed. And over here we have the concentration of N2. Just to the first power. I like that. And let's put some reactants down at the bottom. We have NH3. Don't forget the 2. It's to the second power. All right, very good. So now we have this filled in. We do need to put some numbers in to find out whether or how this relates to our K, which we have given to us, by the way. So let's plug in the numbers for our concentrations. For H2, we had 0.04. That's going to be cubed. For N2, we have 0.18. And down, we have quite a bit higher concentration of NH3. That's going to be 0.7, and we're going to square that. Go ahead in your calculator, do that math. Hopefully you will also find, as I did, that Q is equal to 2.35 times 10 to the negative fifth. What does this mean? Now, be careful. Notice that this is a very small number, and it's very tempting to say, wow, Q is less than 1, so it must be very reactant favored. Well, it just so happens, yes, that's true that there's more reactants. You can see up here we have 0.7 molar NH3, but that's not what Q is for. That's what K is for. The purpose of Q is to compare to K. So let's do that. We have, let's put our Q on the left side. Let's put our K over here. Our Q is going to be 2.35 times 10 to the negative fifth. Am I on the page? I am on the page. And our K is 1.25 times 10 to the sixth. Negative fifth, sixth. So this K value is hugely bigger. So Q is less than K. We can write a little less than sign there. In case there's any confusion about what this actually looks like, this is like 0.0000235, and this one is 1250000. Quite a difference. And just by the way, in case scientific notation ever freaks you out, just do this. It will make it very clear which one is bigger. All right, so Q is less than K. Let's go back up here and see what we have to do. Our goal is to get to equilibrium, right? So if our Q is way too small, we need to make it bigger. How are we going to do that? We're going to take our reactants on the bottom and convert them to products. Or in our equation up here, we're going to take our reactants and we're going to move right and get more of these products. This number up top is going to get bigger, and Q is going to get bigger as well. We can also say that the number on the bottom is going to get smaller, and so again, Q is going to get bigger. That's the plan, so let's write that out. We need more products. And we need fewer reactants. Making little notes like this for yourself, as repetitive as it may seem, will save your life. Or if you're not as dramatic as that, it will help you get points on a test for one semester of your life. Either way is good. All right, so let's do this. Let's make our ice table. Notice that a table was not provided. Well, we can actually rig one up pretty easily just along the side here. And this is actually something I like to do. I'm just going to sort of improvise an ice table like this. Make that over there. Make a few rows. All right, looks good. So I, initial concentration. We have that. C, change in concentration. We pretty much have that, but we need to write it down. And then E, our equilibrium concentration. We're not going to have a number for that, but we are going to have what we call an expression for that. Let's get to it. So for our initial concentrations, let's write those in. We have 0.7 molar over here. We have 0.04 molar there. And we have 0.18 molar over here. Now, when we're looking at this, we have to remember these coefficients. We decided that we need more products. So let's put a plus down here because we know that we're going to be adding something to our products. And let's put a minus over here because we know we need to take away our reactants. I like to go to something that's 1 molar when I start thinking about this. I know that when I'm trying to get to my equilibrium concentration, I'm going to start at 0.18 molar. And then I'm going to add some concentration of N2 such that I get to equilibrium. So we don't know what that number is. We're going to call our unknown number X. Now, if we look at our reaction, we should be able to say, okay, as 1 mole of N2 appears, 3 moles of H2 are going to appear. That's what this coefficient actually means. That while for each 1 mole of N2 that appears, 3 moles of H2 are going to appear. So if we have plus X down here, we need to put plus 3X right there. Similarly, let's go back to N2 again. For each mole of N2 that appears, 2 moles of NH3 had to disappear. So when we are trying to figure out the equilibrium constant of this, the equilibrium concentration, we're going to have 0.7, and then it's going to be minus 2x. All right? So that's basically looking at the stoichiometry, bringing that forward. Most people, I think, usually are pretty good about this part. It's using it as an exponent that gets people. But in case this is your weakness, remember this very well. You just bring the coefficients down. All right, so let's write our equilibrium concentrations now. We don't have an actual number, but basically we're just taking our first 2 rows and putting them together here. Whatever these numbers actually are, once we find X, these numbers represent an equilibrium concentration. So let's say, just as an example, let's say X was equal to 1. If X was equal to 1, that would mean that the equilibrium concentration over here for N2 would be 1.18. That's what that actually means. We're talking about the equilibrium concentrations. All right, hopefully that's pretty clear. Now, let's find K. Or we know K actually, sorry. But let's use K and our calculators to figure out what X is. So we will start out over here on the left side. We're going to say Kc is equal to, given to us is 1.25 times 10 to the 6th. And we're going to set that equal to a pretty large expression over here. Now, again, it's very tempting to skip steps, so I'm going to actually not do that. So let's do Kc is equal to this number that was given to us. Remember, products over reactants. Don't forget those exponents. Can't tell you how many times I've written this down. Well, I can. It's like 14. All right, so products over reactants. And in fact, in case you're not sure, look back to what you did before. It's in the same format as Q. So we've got H2 to the 3rd power, N2, and NH3 to the 2nd power on the bottom. All good, I hope. And now we can put some numbers in. So I'm going to go down a line here. So I'm going to write 1.25 times 10 to the 6th over here. Then I'm going to write an equal sign. Now let's plug our numbers, or our expressions from above, into this equation. Remember, again, these are equilibrium concentrations. Even though there's an X, they still represent equilibrium concentrations. So let's start with H2. H2 is our row over here, so we'll plug that in first. 0.04 plus 3x. And here is where I tend to forget the exponents most. As long as I have my expression directly above, I can remember this cubed. But if I skip a step, that cubed would go right out the window. So beware. All right, N2, here's N2. We found 0.18 plus x. And we're going to divide that by the concentration of NH3 to the 2nd power. So we found that that's the last one over here, 0.7 minus 2x. Quantity squared. Okay, so these are equal to each other, but when we're entering this into our solver in our calculator, because I don't know about you, but when we're dealing with this top part, like mathematically this would be kind of a nightmare. So let's not do that. If you want to see it done mathematically, ask has like Ben to make you a video or something. But yeah, I'm not gonna do that. All right, so let's make the left side equal to 0. We can just subtract both sides by this value, and then the left side of the equation will be equal to 0. So we're gonna take minus 1.25 times 10 to the 6th, and minus 1.25 times 10 to the 6th. This, of course, is going to just be equal to 0. So this ultimately is going to be what we enter into our calculator. So I'll zoom in a little bit and let's see how it goes with me entering in this number into my calculator. Okay, how do I do this? That looks pretty good. All right, there we go. So let's clear all that stuff out. We'll go to math. Okay, so I'll slow down and I'll zoom in just a little bit. All right, that looks pretty good to me. All right, so what I'm gonna do now, actually, hold on. Here, let me show you the buttons I'm pressing just in case. Here's my math button, boop. Then I'm gonna scroll all the way down, oops, all the way down to solver, and there we are. All right, so I have it all in my calculator, and I suppose that I don't need to put this in my calculator again. So if you want to take a look at how I have it entered in, just, pause the video, take a good look. You'll notice I have lots of parentheses, probably more than I actually need. One thing I want to point out is that down here, I was very tempted to put 1.25 to the negative 6th. That's not, times 10 to the negative 6th, sorry. But that's not correct. It's times 10 to the 6th. Remember, we have a very large KC, and I hope I said earlier, but that should imply that products are favored. All right, so that's what we're gonna do. The next thing you wanna do after you've entered that in, go down here, enter in 0, then we're gonna zoom back out so you can see the solving part. Okay, so what we're gonna do is we're gonna hit our alpha button up here, boop, and then down above enter, it should say solve. We're gonna hit enter, and this one takes a long time. Ooh, sorry. This one takes a long time just for it to process. Did it go? There it is. All right, so now we found that x is equal to 0.34963. Yay, we're done. Or are we? No, we're not done. Don't stop with x, please. So what I like to do actually, and you can do this however you want to, but I like to leave a little extra space underneath my e, because once you plug in x here, you're gonna get actual concentrations. And recall that the problem actually wants you to find those equilibrium concentrations. So let's do that. And I'm gonna show you what I like to do as a little bit of a shortcut. So here's my calculator. Here's its beauty mark. It's very nice, right? All right, so for our concentration of NH3, we have 2 NH3, and here's our expression for equilibrium. So let's write that in, 0.7, and then it's minus 2x. Well, believe it or not, your calculator actually has saved the x you just found. Look at my hands. It has saved the x you just found. So if you hit alpha and then go down here to x, right there, so alpha and x, so that it actually says 7 minus 2x, boom, you're going to get a number, and that's actually mathematically calculating it without you having to worry about writing x down again or putting it into your calculator. So I'm going to go ahead and do that for the rest of these values and then put them in. So let's also do 0.04 plus 3x. That looks pretty good. And then we also have 0.18 plus x, like so. And you get that. So we'll enter those numbers into our table here. For the first one, it said 7.396 times 10 to the negative 4th. Just to be absolutely clear that that's not 0, I want to write 0.00074. That's good enough for me. And then for these other two, this one was 1.089, and and this one is 0.529. So just as we'd hoped, just as we'd expected, our reactants are now very heavily favored. You'll notice there's almost no product, or sorry, I said it all backwards. So our products are heavily favored, but we have almost no reactant left. That's good. Based on our very large Kc up here, hey, that's exactly what we expected. Now, the problem is done. We've solved it, everything seems good, but what if we made a calculation error? What do we do? Well, don't worry. There's a nice check for this, and I think it's pretty good. All you have to do is go back. You know what? We already have it written up here, so let's use it over here. Go back over here. Here's our expression for Kc, but we now have found actual numbers. If we didn't make any calculation errors, then when we plug the numbers back in here, we should get our same Kc value. So let's do that. Where should we do that? There we go. All right. So we are going to work with the concentration of H2 cubed times the concentration of N2 divided by the concentration of NH3. All right, so the concentration of H2 we found is 1.089. That's to the third power, you'll recall. The concentration of N2 is 0.529 to the first power, and that's going to be divided by NH3 squared. That's going to be 0.00074. So now you know why I said this is not actually equal to 0, because if it was 0, then we'd be dividing by 0, and that would undo the fabric of the universe. And I'd feel pretty bad if I did that. So let's do this math. We should find, as long as we remember our exponents, this is a 2, even if it doesn't look like it. We should find 1.25, or actually, I'll write out the full number. 1247601. You flip that baby into scientific notation, you get 1.2476 times 10 to the 6th. Let's reduce our number of sig digs, and you get 1.25 times 10 to the 6th. And was that our original Kc? If it is, then it turns out that everything went pretty well, that our math was good, that we didn't forget any exponents. And sure enough, we got the same one. So we did this whole problem, we went through it methodically, and then we double-checked to make sure everything matched up. And hey, it did. Awesome. Which means that this whole problem is a success. And I think that check, I don't know if it's foolproof, but I feel like it will tell you if you've done any major math errors. So now you can relax because you've got these ice tables down. We're going to do more and more stuff with this later in the semester, so if you're confused about the general concept, be sure to come back to this video, leave any comments. But you know, after watching this whole video, you've done a good job, so go ahead, relax. The relaxing tiger, see there? I'm actually not obsessed with tigers, despite what it might seem like, but somebody told me to put tigers in my next video, so hey, look, more tigers. Okay, I think that's about it. Leave questions and comments below. I will be very happy to answer them. And while we're at it, if you have a certain type of problem I haven't done, and you are just like, you have no idea what to do, then be sure to shoot me an email or leave a comment like, would you consider doing this problem? And if I'm not swamped by children or something like that, then I may give it a shot. All right, thanks guys. Have a good time studying and whatnot. All right, later.